Take 15. Hello everyone, today we're doing another fun problem. The premise of the problem is that we have a box or a tube. I wrote it as a box because that's how we draw on 2D drawings. And essentially we have two gases that are split off by a divider and it's closed everywhere else. The gases are going to be gas A and gas B in this situation. Some more given notes is that we have that the whole system, both the pressure and the temperature are constant throughout the entire system. We also know that gas A and gas B are ideal gases. Another thing is that we know this is a closed system, everything's closed around, doesn't open, nothing goes in, nothing goes out outside of the system. Lastly, we know that the molecular weight of A and the molecular weight of B are different. So, knowing that, we're actually here to solve the problem. We want to find the comparison between the molar diffusive flux of A and the mass diffusive flux of A. So, let's start off by writing the equations for both. The molar diffusive flux of A is actually equal to the molar concentration of A times the velocity of A minus the total molar velocity of the entire system. So, next we have the mass diffusive flux of A, which is equal to the mass concentration of A times the velocity of A minus the total mass average velocity. So with these two, we can use these two equations to find the comparison between the molar diffusive flux and the mass diffusive flux. So let's start off by figuring out ways to put these together. We'll start off by getting rid of, and I say getting rid, we're not really getting rid of them, we're kind of changing them around so that we can mix both of these equations together. We're going to mix around the molar average velocity, the total molar average velocity, and the total mass average velocity. So let's start off with the total molar average velocity. We know that the total molar average velocity fits into this equation, which is the total molar flux equals the total concentration, total molar concentration, times the total molar average velocity. We also know, by looking at the problem that we have here, that when we break this open, concentration B and concentration A will be going against each other. Their fluxes go against each other. So with that, we can actually find the molar flux, because that is just the sum of the molar flux of A and the molar flux of B, which, since they're both the same, they're going at each other, that will just end up equaling 0. With that, we know that the concentration, the molar concentration times the total molar average velocity will also equal 0. I'm going to go ahead and erase this bottom part. Knowing that, we know that either the molar concentration or the total molar average velocity has to equal 0. Well, it can't be the concentration, therefore it has to be the total molar average velocity. Therefore, we know now that the total molar average velocity must equal 0. We can take that and substitute it back into this problem right here, and I'll go ahead and rewrite it up here, that now we have the molar diffusive flux, the molar diffusive flux of A is equal to the molar concentration of A times the velocity of A, because that is 0, subtracts, goes away. With that, we're actually going to rewrite it down here and save that for later. But we're also going to rewrite it in a different form to the right, because we can use something from this, and that will be the velocity of A. If we rewrite this, we can rewrite this as it being that the velocity of A is equal to the molar diffusive flux of A over the molar concentration of A. The reason we need that is coming up with the next one, where we go and focus on the mass diffusive flux of A. So in the mass diffusive flux of A, we're going to kind of expand it a little bit and multiply this mass concentration to both of these. And we have that it is the mass diffusive flux of A equals the mass concentration of A times the velocity of A minus the mass concentration of A times the total mass average velocity. The reason why we're writing it like this is because then we can look at over here, we have that the velocity of A is equal to the molar diffusive flux of A over the molar concentration of A. So we're going to rewrite it like that actually. But we're going to actually split these apart so that we can see something. And I'll show you that in a minute. We can see that we actually have the mass concentration of A over the molar concentration of A, which if we put those together, all that really is just the molecular weight of A. So we can go ahead and substitute this and get that the mass diffusive flux of A is equal to the molecular weight of A times the molar diffusive flux of A minus the mass concentration of A times the total mass average velocity. So we're actually going to take this equation and write it down here too and kind of save it for a little bit. So we're going to work on something else. I'm going to go ahead and erase all this. But we are going to keep that there because we're going to need it in a minute. So right now what we need to do is we actually need to figure out the mass average velocity, because I said we're going to have to get I say get rid of these, you're not really getting rid of them, you're changing them around. So we're going to change around that mass average velocity. Oh, wrong color. We're going to go ahead and change that mass average velocity to find the equation that the mass average velocity is actually just the velocity of A times the density, the mass concentration of A plus the velocity of B times the mass concentration of B over the total density. So we have that main equation there. But we can actually figure out what the velocity A and the velocity B are through this equation. But how can we find B? It's actually just going to be the same exact thing. It's just going to be the velocity of B is equal to the molar diffusive flux of B all over the molar concentration of B. So now we have the velocity of B and the velocity of A, which we can substitute into this equation. But again, I'm going to actually take the molar concentrations and kind of separate them apart and write them as 1 over the molar concentration, and I'll show you why in a minute. So now we have that the total mass average velocity is equal to the mass concentration of A times 1 over the molar concentration of A times the molar diffusive flux of A, which is added to the mass concentration of B times 1 over the molar concentration of B times the molar diffusive flux of B all over the total density. The reason why we separated this again is actually we've already done it before, where we know that the mass concentration of A or the mass concentration of B all over the molar concentration A or the molar concentration of B actually just equals the molecular weight. So we have from here, we can find that this is the molecular weight of A and this is the molecular weight of B. Using that, we can rewrite this as mass average velocity, the total mass average velocity is equal to the molecular weight of A times the molar diffusive flux of A plus the molecular weight of B times the molar diffusive flux of B all over the total density. Now, from here we still have one more step to do, and that is we are not solving or trying to compare, we're not comparing at all the molar diffusive flux of B. We're trying to find the comparison between the molar diffusive flux of A and the mass diffusive flux of A. So we actually kind of need to get rid of that. Again, not get rid of it, but we're changing things around. Actually, we can find out that through knowing that the sum, actually I'll rewrite this on the top here, so that we're wearing red. We know that the sum of the molar diffusive fluxes all around has to equal 0. Knowing that, we know that the sum of the molar diffusive flux of A and the molar diffusive flux of B must equal 0. With that knowledge, we can actually find out what the molar diffusive flux of B is, because all we have to do is subtract the molar diffusive flux of A, and we get that the molar diffusive flux of B, and sorry for it being a little curved, is the negative of the molar diffusive flux of A. So we're going to go ahead and substitute that right into there. I'm going to rewrite it up top here. So we have it that the mass average velocity, the total mass average velocity, is equal to the molecular weight of A times the molar diffusive flux of A plus, there's a minus there, so we subtract it now, minus the molecular weight of B times the molar diffusive flux of A. So we successfully got rid of the molecular diffusive flux or molar diffusive flux of B. And this is again all over the total density. I'm going to go ahead and erase this bottom part and this side part. So we still have a little bit more work to do. Very simple from here. Now that we have this, we can actually simplify this just a little bit further and get that the mass average velocity, the total mass average velocity, is equal to the molar diffusive flux of A times the differences between the molecular weights, and all that again is over the total density. Now that we have this, I'm actually going to rewrite it down here. We're going to play with it right now, but we're going to rewrite it for now. So from here, I'm going to go ahead and rewrite the equation to the mass diffusive flux of A. And lucky us, we actually found a way to substitute the total mass average velocity with the equation we just created. So we're going to go ahead and substitute that. do, we're going to write the density as 1 over the density. We're not going to write it as this full thing. We're going to have it separated, and I'll explain why in a minute. So now we have that the mass diffusive flux is equal to the molecular weight of A times the molar diffusive flux of A minus the mass concentration of A times 1 over the density, the total density, times the molar diffusive flux of A, which is multiplied by the differences of the molecular weights of A and B. The reason why we wrote this separately is, again, we have right here, we have the mass concentration, which can be put over the density, and we can rewrite that because we know that the mass concentration of A is equal to the mass of A over the total volume, and we know that the total density is equal to the mass over the total volume, which, I'm just going to draw it right here, if we put over each other like this equation shows, we can actually get rid of that volume, the total volumes, which leaves us with the mass of A over the total mass. The mass of A over the total mass is really just the mass fraction of A, which we can now use this to substitute it back up in there. So, I'm going to rewrite it, this as the mass fraction of A. So we get, give me just one moment to write it down, we get that the mass diffusive flux of A is equal to the molecular weight of A times the molar diffusive flux of A subtracted by the mass fraction of A times the molar diffusive flux of A multiplied by the differences of the molecular weights of A and B. But we can do this just a little bit further actually. We can take out these molar diffusive fluxes and get that the, give me just one moment to write it. So we can get from that the mass diffusive flux of A is equal to the molar diffusive flux of A, but that is multiplied by the molecular weight of A subtracted by, and this is all in parentheses, subtracted by the mass fraction of A, which is multiplied by the differences of molecular weight of A and molecular weight of B. And that is where you end the parentheses, and I will circle it 3 times with 3 different colors for everyone to see. This is the comparison that we were looking for of the molar diffusive flux of A and the mass diffusive flux of A. That is right there, there's the equation.